Hey all, today we're going to talk about the normal model and a little bit more about z-scores in reference to the normal model. So if data has a distribution that is approximately unimodal and symmetric, unimodal and approximately symmetric, then we can use what's called a normal model to sort of make some comparisons between data points. The technical way that we write that something is approximately normal, or we're using a normal model, is this up here, capital N, in parentheses, mu and sigma. And remember, mu, the Greek letter mu, represents mean. The Greek letter symbol sigma represents standard deviation. And so the important things to know about a specific model is what is its mean and what is its standard deviation. And you should remember that when we calculate a z-score, those are the two pieces of information we absolutely need. In order to use a normal model and to use the processes we're going to talk about today, you need to check what's called a nearly normal condition, and that is that the shape of the data is unimodal and approximately symmetric. I'm going to type approximately. And so if the data is like that, unimodal, approximately symmetric, then we have something that looks like this. You might have referenced it, talked about it as a bell curve. This is a normal curve. The mean is right there in the middle. It's got two tails. And 68% of the data falls between one standard deviation above or below the mean. And the area underneath the curve between these 2 points, minus one standard deviation and plus one standard deviation, represents the proportion of data points that will fall between those two. 95% of the data will fall between two standard deviations. And then lastly, 99.7% of the data is within 3 standard deviations from the mean. So 0.3% of the data is further out. And I mentioned in class that things are unusual or unlikely once we get past 2 standard deviations. We would consider something less than 2 standard deviations below the mean, greater than 2 standard deviations above the mean. A situation like that would be unusual. And you can see here that there's not very much area underneath the curve in those two tails. And so it's not likely that something that far away from the mean will happen. That'll make more sense in context when we do some examples. So take a second and read this. This is from the book. Take a second and read it, and we'll have a discussion. So we're saying that the mean on the SAT reasoning test is 500, and the standard deviation is 100. We want to know if you got a 600 on one part of your SAT, where would you stand among all the other students who took that test? And so the first thing we always have to do if we want to use a normal model to talk about something is we need to check the nearly normal condition. And I believe they say in here that it's roughly unimodal and symmetric. And so if we're doing a problem that says that, we are allowed to use the normal model. So you can sketch a normal model. I've cheated a little bit and borrowed a picture from the book. The mean goes right in the middle, 500, and then the standard deviation is 100. So if we add 100 once, twice, and 3 times, we can see 1 standard deviation above, 2, and 3. Subtract 100, we get 1 standard deviation below the mean, 2 standard deviations, and 3. And so again, 68% of SAT test takers here should fall between 400 and 600. 95% should fall between 300 and 700, and 99.7% of the test takers will score between a 200 and an 800. Again, it would be considered unusual to get between 2 and 300, considered unusual to get between 7 and 800, and even higher or lower. So if we got a 600 on the test, we would be 1 standard deviation above the mean. And so we could actually say that, we could actually say that, let me get my pen. Since there's 68% between 400 and 600, and there's 50% below 500, so we have 50% of the data on this side, and between 1 standard deviation above and below is 68, that this area is half of that, so 32%. So this whole area I colored in is 50 plus 32 is, oh, I'm sorry, 34. Hopefully you're at home correcting my math before I am. So that area under the curve I colored in is 84% of the area. So I actually did, or the person who earned a 600 actually did better than 84% of other students. We can standardize distributions that are normal models that are approximately symmetric and unimodal. And so when we standardize them, converting all the data points to z-scores, we get a model that has a mean of 0 and a standard deviation of 1. And so my mean would be 0, and my standard deviation is 1. So right here would be a z-score of 1. Here would be a z-score of 2, 3, -1, and -2. So when we calculate those z-scores, they're actually related to a standard normal model, a normal curve, a bell curve, that we've transformed this axis to be z-scores. So we can find area under the curve using a standard normal model, calculating some z-scores. So using our SAT information, mean 500, standard deviation of 100, I want to know the proportion of students who score between a 450 and a 600. Oops. So we checked our normal condition already. We're using the same information. We know that this is can be a normal model used here, but it's good to keep thinking about that. We're going to have to check conditions a lot this year. And now I can calculate z-scores for both of the 450 and the 600. Just using the z-score formula we used in the last lesson. And now I want to draw a picture. I always want to draw a picture. It helps to have a visual in this class. And so if I draw a bell curve or a normal curve, even though mine looks awful, it's okay. The mean is in the middle. If it's a standard normal model, the mean is 0, standard deviation is 1. And so that means my z-score of 1 over here is 1 standard deviation above the mean. Z-score of -0.5 is to the left. It's half a standard deviation below the mean. And this area in red represents all of the people who, or the proportion of people who would score between 450 and 500, who would score between z equals -0.5 and z equals 1. So I'm looking for a proportion or probability that somebody scores between 450 and 600. We transform those to standard z-scores, so we can write that as the proportion somebody scores between -0.5 and 1, and now we can calculate that using technology. So I'm going to hit the second button and then the VARS button, and above that it looks like distribution, and so we're talking about a normal distribution. And we're going to choose normal CDF, and lower and upper mean lower bound and upper bound. So what is the lower part of the area I shaded in? Well, that's negative 0.5. We're plugging in z-scores. My upper bound is 1, a z-score of 1. You can see my default is a mean of 0, a standard deviation of 1. And then I can hit enter twice, and I get this decimal, 0.5328 approximately. And what that means is that 53.28% of SAT scores will fall between 450 and 600. So we can also go in the reverse, and I know we're going kind of quick, we'll have time to practice. So this time I want to know what SAT score equates to the top 10%. So again, we're using the same mean and standard deviation, mean of 500, standard deviation of 100. So we're nearly normal, we already know that, and I'm going to make a picture. My standard normal curve, my mean is 0, standard deviation is 1. 10% is going to be up here to the right. We're talking about the top 10%, so to the right. And that means all the stuff to the left is 90%, the stuff that's left over. And I want to know what z-score is associated with 10% here on the right-hand side. So I'm going to use my z-score formula, and I'm going to plug in mean and standard deviation. And I can find the z-score associated with 10%, again, by using technology. I'm going to hit second vars. We're still looking for distributions, and this time I'm going to do inverse normal, choice 3. We're doing the opposite thing we just did. And it's gonna want you to tell how much area is to the left of the z-score you're interested in. So we are looking at the top 10%, but the area that's to the left of the z-score is 90%, so I'm going to do 0.9. We've got to put it in as a decimal. Leave our mean and standard deviation as 0 and 1. And we get a z-score of 1.28. And so I can plug that into the formula and then solve for x, x being the data point that would represent a z-score of 1.28. And I get that so a person with a score of 628 on the SAT is in the top 10 percentile. And so anybody with that score or higher will be admitted to this college. So that might have been a lot. I don't have any questions for you again today. We can do some practice in class, and if you have questions, please be ready with them at the beginning of class.